In this section, we're going to talk about parent functions and their respective transformations. Right now, we're going to focus on these 4 parent functions. There are more, but most importantly, we're going to focus on these 4. And our first function is the absolute value of x, and its respective graph is this. Again, the absolute value of x and its graph. And our second function is x squared, or x to the second power, or also known as quadratic equation. And right here is its respective quadratic graph. And the third one is x to the third, or x cubed. And right here is the respective cubic function graph. Last one is the square root of x. And right here is the square root function graph. Now, if you take a look at each of the 4 equations, you notice that there are no numbers in the front, no numbers within, and I'm excluding the exponents. The exponents are used to describe types of function. Square for quadratic, cube for cubic. Now, again, there are no numbers within the function, and there are no numbers after the variable x. So, if there are no numbers in the front, within, or after the function, or after the x, then there are no transformations. These are what the parent's function look like, or the original functions. Now again, the exponents are excluded, so they don't count as numbers. In addition, numbers can be counted as whole numbers or fractions. So keep in mind, we're going to see whole numbers and fractions when it comes to transformations. In this first part, we're going to go over translations. That's talking about how the graphs move vertically or up or down, and horizontally, meaning left or right. Now we have 2 examples here, and I will show you how I'm going to do the work to show you the graph and then talk about the transformation, and you will visually be able to see what's going on. So our first step, when you have the absolute value of x plus 2, so you have a number within the function, what we're going to do is we're going to look for the vertex. So in order to find a vertex, we have to find the x-coordinate of the vertex. So in order to find the x-coordinate of the vertex, what we're going to do is you set the inside equal to 0. So since it's x plus 2, again, this function is the absolute value of x plus 2. We're going to set x plus 2 equal to 0. Again, this is for the x-coordinate of the vertex. So x plus 2, we're going to solve for x, and we get x equal to -2. Now, that's the x-coordinate of the vertex, and vertex is a coordinate point, x and y. So that means we need to find our y. So what I'm going to do is set up a xy table with this in the center. So let me choose a different color, easy to see. So here's our xy table. Now, if we go back to the parent function of absolute value, we see it's a straight line. So that means that we would need at least 3 coordinate points in order to graph. So you could do it with 4, you could do it with 5, but we just only need 3. So our vertex will go in the center, in the middle, and that's our x-coordinate of the vertex. So I'm going to put -2 here. Now, this is the easy part. For you to determine the other coordinates, you need to determine the other x-coordinates. So since this is in the middle, here could be one less or one more. So I'm going to do one less of -2. One less of -2 is -1. One more, well, actually, less, when it comes to a negative number, less goes in the opposite direction. So one less of -2 is actually -3. Now one more than -2 is going to be -1. So one more of -2 is -1. One less of -2 is -3. Alright, so now we're going to do the work to find the y values. So what I'm going to do here is use this function. So I'm going to write it right here. Now, even though it says f of x, we can switch it out with y, because that's what we're looking for our y value. So y equals the absolute value of x plus 2. Now we're going to plug in -2 in because that's our center. So I'm plugging -2 here. And then inside it's -2 plus 2, so that's going to be 0. Now it still has the absolute value. And then the absolute value of 0 is just 0. So I'm going to write 0 here. Now you can either do -1 or -3 next. Doesn't matter. So we're going to plug in -1. I'm just going to say x equal -1 to organize my work. So x equals -1. So I'm going to plug in -1 into x of the function right here. And then the absolute value. -1 plus 2, well, that's just 1. And it still has the absolute value. And then the absolute value of 1 is just 1. Again, the absolute value makes the inside number becomes positive. Since it's already positive, it just be the same number. Now, well, actually, let me put it right here. 1. Next, I'm going to plug in x equal -3. So we're going to plug in x with -3. So -3 here plus 2. Now -3 plus 2, that's going to be -1. So the absolute value of -1, again, what I said before, absolute value makes the inside number becomes positive. Again, absolute value makes the inside number become positive. So since it's -1 and the absolute value of it, it should be 1. So there we go. Now we have three coordinates of this function. So what I'm going to do is going to mark these three coordinates right here onto this graph. So -1, 1. So here's -1 and 1. So I'm going to mark it right here. And then -2, 0. So -2 for x and 0 for y. I'll mark it right here. And then -3, 1. So here's -3 and here's 1. So again, even though these counts by 2, there's a line for -1, there's a line for -3, there's a line for -5, line for -7. -1, -2, -3, -4, and so on. But here's our three coordinates. And again, here's the absolute value graph, or the parent function of absolute value. So I just gotta make it look like that and connect the dots. So here is the left side of the function, and then here is the right side. Alright. Now if we compare it with the parent function, so we see that the parent function is going through the origin. But here, the absolute value of x plus 2, we see that from the origin, it translated or it moved 2 units to the left. So parent function went through the origin. The transform function translated or moved 2 units to the left. So if it's plus inside, so plus 2, that means that it's going to move 2 units to the left. Now let's talk about our second example. The square of x minus 3. Again, this is the square of x minus 3. So what I'm going to do is the same process for this example. Now in example 2, we have the square of x minus 3. Now notice how you have parentheses on x minus 3 with the square outside. If you go back to the parent function, x squared, there is no parentheses, because since there are no numbers in the front, within, or after, you don't have to worry about parentheses. But since we actually have a minus 3 within the function, we have to include parentheses, saying that the square is affecting the whole function of x minus 3. So we're going to do the work and see what's the transformation when it's x minus 3. So same thing as the last example. Since this number within the function, we have to set this equal to 0 in order to find the x coordinate of the vertex. So we're going to do x minus 3 equal to 0, and then solve for x. So I'm going to add 3. Now it's x equal to 3. So that's our x coordinate. So we're going to do the same thing as before and make our xy table. Alright. Now, same thing as before. Here's the quadratic graph. Now, even though it's not like a straight line as the absolute value, you can imagine that it's a U shape. So, again, we just only need at least 3 points. You could do it 4 or 5 or more to be precise. But again, I'm not looking for precise, I'm just looking for close to precise. So again, we just only need 3 points. Since our x coordinate of the vertex is 3, I'm going to put it in the middle. Now, again, we just need the number next to 3. So, number that is 1 less than 3 is 2. One number more than 3 is 4. Just like before, we're going to plug in all of these x coordinates and get a y value. So, even though this says g of x, we can replace it with y equal the square of, so be very careful when I'm saying square of. So this means the whole thing, x minus 3 is being squared. So it's the square of x minus 3. So we're going to plug in 3 first. So here's 3. So 3 minus 3, that's 0. Now I'm going to keep the parentheses because it's the best habit to have, especially when you have a number in the front, including, and most importantly, if it's a negative. So 0 squared, that is just 0 times 0, and that's 0. Alright, now we're going to do 2. So I'm going to organize my work, x equals 2, and I'm going to plug the 2 into that x. So 2 minus 3 squared. Then I'm doing 2 minus 3, which is negative 1 squared. Especially when we have a negative 1, it's a good thing to have parentheses, especially when we're going to be working with calculators. So we got to be careful how we put our parentheses. So when it's negative 1 squared, it means negative 1 times negative 1. Negative 1 times negative 1 is a positive 1. So I'm going to put 1 right here. Now we're going to do x equals 4. Okay, so 4 minus 3 squared. So 4 minus 3, that is just 1. Now even though it's just a positive 1, I'm going to keep good practice and include parentheses. So 1 squared, it just means 1 times 1. So 1 times 1 is just 1. And I'll put it right there. Alright, we got our 3 coordinates. Now it's time to graph. And again, it doesn't have to be precise. It just has to be close to the parent function right here. So start with 3, 0. So 3, 0, it's 0, 1, 2, 3 right here. Next, 2, 1. So 1, 2, and then up 1. And then last one is 4, 1. So here's our 4, and here's 1. And again, it doesn't have to be perfect. You just have to look close to it. So I'm going to try make it a U shape. And it doesn't have to go all the way to the top. Just have to be close to it. Alright, so here's the transform graph, and here's the parent function. We see that the parent function went through the origin 0, 0. Now if we look closely right here, we see that it shifted, translated, or moved 3 units to the right. So here's 0, the origin, and we see that it went 1, 2, 3 units to the right. And here is touching the x-axis, just like the parent function is touching the x-axis. So when it's x minus 3, it means that it shifts, or translated, or moved 3 units to the right. Example 3, we have h of x equals x to the third plus 4. Now, here, the x does not have parentheses, meaning that there is no number within the function. But we do have a number that's after the function, the plus 4. So, just like in the last example, it had x minus 3 parenthesis squared. That minus 3 was within the function. Here, there is no number within the function. So, since there are no numbers within the function, you can safely say that the x coordinate, I'm going to write right here, x coordinate of vertex. So the x coordinate of the vertex, we can safely say that x equal 0. And just like the last 2 examples, we just need 3 points. Like I said before, it doesn't have to be a precise graph of this parent function, this cubic parent function. So once we get our x coordinate of the vertex, we just need to make a x, y table. 1, 2, 3. Boom. Alright, so again, the x-coordinate vertex will go into the middle, so 0. Now we just need one number less than 0, which is -1. And then we need one number higher, so that's 1. Alright, so once we get our 3 x-coordinates, we're going to plug it into this function. So instead of h of x, I'm going to say y. Y equals x to the third plus 4. So we're going to start off with the x-coordinate of vertex, which is 0. So again, just like in the last example, I'm going to include parentheses for good practice. So 0 parenthesis to the third power plus 4. Now it's to the third power, so it's 0 times 0 times 0. 0 times 0 times 0 is just 0. So 0 plus 4 equals 4. So I'm going to write 4 here. Now we have a -1. So this is why we're going to include parentheses. So first off, I'm going to write x equal -1. And plug it into this function. So y equals -1 parenthesis to the third power plus 4. Now I'm going to show you the work so that this is how negative number works, and we have to be very careful when we have negative numbers. So -1 to the third power is just -1 times -1 times -1, and then plus 4. So we're going to take it step by step. What I'm going to do is show you that I'm going to multiply the first two -1s. So -1 times -1 is a positive 1. And I bring down that -1 and that plus 4. Now we're going to work with 1 times -1. And I suggest doing this process when you're working with, say, -2, -3, and higher numbers of it. So 1 times -1 is -1, then plus 4. So -1 plus 4 is 3. So I'm going to write 3 right here. So here's the work when x is -1. Now I need to make room for x equals 1. So x equals 1. And then I'm going to plug 1 into x. And I did the same thing, I incorporate parentheses. Now, even though it's just 1, it's good practice to write it out. So to the third power, 1 times 1 times 1. Now the reason is because I want y'all to see what work you're doing, especially if you want partial credit. This will help you out visually what you're doing. So I see myself multiplying the 1s 3 times. So I don't want to get confused with square. So I'm going to say to myself 1 times 1 times 1. So 1 times 1 is just 1. And then times 1 again is just 1. And then plus 4. So which is 5. Now again, I'm doing this practice in case you have like 2 to the third power or 3 to the third power. Now I had students that confuse with numbers to the third power with numbers that are being with the second power. So once we get our 3 coordinates, I'm going to mark it in this graph. So our center is 0, 4. So 0 for x and then 4 for the y. So one coordinate is -1, 3. So here's -1, and then here's 3. And then here is 1, 5. So 1, and then 5 up here. And again, it does not have to be a perfect graph like this, just close to it. So I'm going to graph it looking very similar. It doesn't have to be precise or just close to precise. So I'm going to graph it like this, curving. And then I'm going to graph the other end, curving, going through the point. Now again, it does not have to go all the way down, just looks similar to it. Now, I didn't decide to do 5 points because if I were to do 2 more points, the 4th and the 5th points, well, the 4th point you can see it on this side, but the other side you can't. It will go beyond the graph and it's going to be hard to graph precisely or to see visually. So if we look at the parent function, we see that it's going through the origin. Now we see that it's not. If we take a closer look, here's the origin, 0, 0, and here, right here, it's not. We can see that it translated, it moved 4 units up. So this transformed graph translated, shifted, or moved 4 units up. So if it's plus 4, it means that the graph will move, translated, or shift 4 units up. Example 4. M of x equals the square root of x minus 5. So just like in the third example here, there's no number within x. There's no numbers within the function. So we can safely say that the x-coordinate of the vertex will equal to 0. So I'm going to write right here, x equal to 0. So again, since there's no number within the function, the minus 5 is after the x, is after the function. So since there are no numbers within the function, we can safely say that x is equal to 0 for the vertex. The x-coordinate of the vertex equal to 0. Now, same thing as before, xy table. So, x, y. 1, 2, 3. With the x-coordinate of the vertex in the middle. So I'm going to put 0 here. Well, wait a minute. This is a different function. It has a square root. So let's go back. Here's the square root function. Then we notice that these 3 functions here has a center or a vertex. Vertex, vertex, vertex. But this one does not. So what happened is, since the square root of x does not have a vertex, that means we can't put the 0 in the center. So that means we actually have to start off with 0. So what I'm going to do first is going to plug 0 into x. So I'm going to write y equal the square root of x minus 5. And then I'm going to plug 0 in, so x equals 0. So y equal the square root of 0 minus 5. And the square root of 0 is just 0. And then bring down to minus 5. So 0 minus 5, it's negative 5. So I'm going to write negative 5 here. Now, the tricky part, or I would say the confusing part, is you have to think of numbers that you can plug into x, and it has to be able to be square rooted. So what numbers can we put in that you can square root of? That means it has to be a perfect square numbers. So in this case where x is by itself, there's no number within the function, that means you can use perfect square numbers. Perfect square numbers are, besides 0, 1, 4, 9, 16, 25, and so on. Those are examples of perfect square numbers. So in this example, we can use perfect square numbers, but there are going to be other cases where you cannot use perfect square numbers. You have to make it become perfect square numbers. But in this case, we don't have to. So let's see, we already did 0. Our next one, it could be 1, so we could use 1. So I'm going to write x equal to 1, and I'm going to plug 1 into x. So y equal the square root of 1 minus 5. And the square root of 1 is just 1. And then 1 minus 5 will be negative 4. Alright. Now we already did 1 as the perfect square number. Our next one will be 4. So we're going to plug 4 into x. So x equal 4. So y equal to the square root of 4 minus 5. And the square root of 4 is just 2. And bring down to minus 5. So 2 minus 5 will become negative 3. So I'm going to write negative 3 here. Alright, we got our 3 coordinate points. So we're going to graph over here. So our first coordinate point is 0, negative 5. So 0, negative 5. It's going to be right here. Next one is 1, negative 4. So 1 and then negative 4. Our third one is 4, negative 3. So here's 4, here's negative 3. Just like in the last 3 example, we were only using 3 coordinate points. But if you like to be precise, you can use more. And now we're just going to make it look very similar to the parent function. So I'm going to start off with our first point right here. So I'm going to connect the dots and extend. Doesn't have to be all the way, but very similar. Now notice how I didn't go past the first point. So if that's the first point, we're going to start here going to the right. But there's going to be other transformation where you would start with the first point and maybe move to the left. But right now we're not going to talk about that. We were working with this example. So here's the parent function at the origin 0, 0. Here's the transform function that is not. So if I show you the equation, the square root of x minus 5. This one does not have minus 5. So if we take a comparison between these two, we notice that here the parent function is at 0, 0. Here it is not. We see that change was that it shifted, translated, or moved 1, 2, 3, 4, 5 units down. So again, if it has a minus 5, it means that it shifted, translated, or moved 5 units down.